So, think now the microphone is working. Hello, everybody, and um, so back again to the series of building my own AI chip. So, starting from the very scratch, which is like the language that is used, how to think of building a chip. So, um, I after a long search, I end up choosing this tutorial over here, and until now it looks very interesting. So from the beginning, tell me about the task, which is like building calculator. But now, of course, the calculator is gonna be built on software side, as most of people would have already built by using Python. But it will be built on the hardware side, in which it is connect circuits, and of course, we're gonna be using Systemverilog to build it. And then the looks like the AI who is talking with me now start to tell me how to think in order to fulfill the task, which is building a calculator by using System Verilog, in which the very first part would be thinking of what kind of blocks um, the functionality can be represented by. So dividing, so basically, any hardware developer, the first thing that a developer think of would be the requirement. Okay, building calculator. So what is this calculator consists of? What is the basic, the blocks of it that represents it, the functionality? So yeah, it need a counter, but actually we need counter was okay, but it wasn't the perfect answer. It's from the AI, so it looks like we need to think from very higher level. So we need to perform calculation itself. We need to get data from the user. We need to convert the data that the user will be giving. Um, so the user, I can imagine calculator has buttons. So the user press in buttons to write 3 or 4 or 7 or 15. And then the logic has to detect that it is 15. So it's like converting from signal into the ASCII number that represent the number itself. And at the end, it should perform after performing the calculations to make that display. So all of that are mostly blocks that are in some point connected to each other. And then, yeah, the hardware developer will then build an RTL block diagram from all of that. And then after that, he will start to perform the coding. The first part is to think of the models to represent each and every of these aspects. So a model for adding, for example, so for the software programming people, I can imagine that like module is more or less like a functionality, and like a function, right? That has also parameters. But again, here, so it's like module and then a module name. And then inside the parameter itself is the inputs and output signals. And here I am trying to figure out, I stopped last session in trying to figure out what is the correct syntax in determining the um, like the range of the bit widths of the inputs and the output signal. So he told me, like, let's say the range is, or the width of an input signal is 8 bits. So what is now the range, right? So what is the syntax to describe it? So without me cheating and looking it up on the internet, I imagine the syntax would be uh, input input signal called A, input signal called A, and then it has a range from 0 till 8 bits, 0 till 7, right? It's 8 bits. And this is my definition of the signal. Let's see if it's correct. You are very close, from 0 to 7, correct. Indicates the range of bits in System Verilog when declaring multi. bit signal, you typically specify the most significant bit first, followed by the least significant bit. So, mm, okay, so most significant bit and then the least significant bit. It's like writing in Arabic, right? So you write from right to left. So the most, the end of it, until the beginning, the least. So how would you write the full declaration for an 8-bit input A within the module, defining including the input key and logic type, which is commonly used for signals in modern system Verilog. So I have to correct myself now. Looks like it's an input keyword because it's an signal. And instead of signal, they syntax it as a logic and the name of it, and then from the most significant to the least significant. Here we go. Let's see. Excellent input logic from 7 to 0A is the correct way to declare IP input named A in System Verilog. This specifies that A is a logic type signal and it has a width of 8 bits, index from 7 down to 0. Now that we have covered data types and modules declaration, let's move on to using array loops for efficient design. Imagine you need to implement a calculator that can store several previous results. How might you use a system Verilog array to hold, say, the last 8-bit results? The last 4 8-bit results. Okay. So basically, what he's saying is like, okay, let's imagine I made a calculation from 1 time 1, 1 time 2, 1 time 3, 1 time 4. So it's like the results are 1, 2, 3, 4. So how can I save them in an array? So of course, my array, not sure how to make an array now. So let's call it array results. And they are 4. Um, I think from 3 to 0. Mm, or is it 4? Array 4 result. All right, let's see. So this is my imagination. I've got the right idea. So results being an array of size 4, however, just like with single signal, you need to specify type and bit width of each element in the array, right? So would you declare an array named results that can hold 4 8 bits logic values? So I think array um, was 4 8 bits. So I know that 8 bits will be from 7 down to 0. And the array called results, but how can I specify that it is 4? Maybe like that, because the size is 4. It's very close. You have correctly placed the bit width 7 down to 0 and the array size to 4. System Verilog, in System Verilog, the bit width typically comes before the signal name, all right? And the array dimension comes after the signal name. Also, you need to specify the data type, which is logic also, so it's a signal in In this case, how would you combine logic results and for to correctly declare for an array of 4-bit logic? All right. So basically, it's a logic, and he said that the size comes first, and then the name, and then from 7 down to 0, not to 9 to 0. Let's see. You're almost there, but the order of the array dimension and the bit width is still a little mixed up in Verilog. Remember, the bits width 7 applies to each element within the array, and the array dimension is 4 defines how many of those elements there are. Think about it this way. You are declaring a collection of 8-bit logic value. How would you write that declaration? The bit which usually comes right after the logic word. This is what I have made at the beginning. The array dimension comes after the signal name. All right, so this is exactly what I have made at the beginning. It's like, so bit width usually comes after the logic, and this is what I have made it here. Bit width after, yeah, okay, so it's logic maybe. Okay, so basically gonna be writing a logic, and then the same like any other signal from 7 down to 0, core results. Then afterwards we have it, the size is 4. Perfect, wonderful. So this makes sense actually, and this is what I have made actually in the beginning, but looks like it reacts a little bit. Yeah, that's very close. So yes, keep telling me here. So I didn't make any changes. I just changed the word array to be signal, array to be logic, which also makes sense. So, oh wait, oh yeah, here. So actually, I'm not very satisfied with the answer of the AI, but I at the end I just got the idea of how to make an array. So here we go. So without that one, it's a kind of one variable, but with this syntax, then it is 4, right? Size 4 array. Now let's think about how loops can make our design more efficient. Imagine you have the results array, and you want to initialize all 4 elements to 0. How could you use a for loop in Systemverilog to do this efficiently rather than writing so? All right, makes sense. So I believe, I don't know, maybe loop for, does it have a start and then maybe start? I don't know. Start loop for, um, I think start loop, and then we have for loops, and then, oh, wait. That was, I do not want to. All right. You are thinking about the right construction. A for loop is exactly what you need to write a for loop in Systemverilog. You will need a loop variable, often I, a starting condition and an ending condition, and an incrementing step inside the loop. You will then assign 0 to each element of the result array. How would you write for loop? All right, so it reminds me a little bit maybe of C++, in which we have here a for loop of, yeah, I, which should be again logic and 8 bits down to 0 called I. Um, yeah, this is typically C++, so I'm not sure if it is really what it is needed here, but well, let me continue. So this is the I, so this is the condition, I less than 4, and then I plus plus. Doesn't make any sense, to be honest, but let me see how it will react. Very close for loop instruction. You are correctly identifying the loop condition. That's amazing. Incrementing also. So it's basically the same like C++, in which we write a condition. However, there are a couple of small adjustments needed for the for loop variable declaration and how you would use it to access the array. In Systemverilog, it's common to declare the loop variable I as an int or integer for loop. Makes sense. You don't need to specify its bit width like 7 to 8 unless it's directly representing hardware signal of the width. Also, the initialization of I is missing. That's correct. How would you write the for loop to initialize I to 0? Uh, Loop while I is less than 4 and increment I by 1 each time, and then use I to assign 0 to each element, resulting. So then it's very simple. This happens when you overthink your life, right? So I um less than 4, I plus plus from 0 to 3, and then here we can then write you remember the results of 0. Oh, and then it will be of I equals to he said everything should be 0, right? Then semicolon. So this is how I would write it in C++. Let's see if it is really fulfilling the needing. Excellent. All right. So uh looks like I have done an amazing work here. So begin. So wait, so basically we have here, so instead of brackets, I need begin, right? And then I need to define it, and then I need an end. Is a perfect way to initialize an element in your results array to 0 using a for loop in Systemverilog. You have correctly used int in the for variable to set up the condition and access the array element. This demonstration demonstrates a strong understanding of how you use a for loop for efficient hardware description. Good job. You have completed all the topic of our session. Up next, view your feedback. Wonderful. So I give it a wonderful feedback, and I really like your um, understanding of the language. All right. So during today's session, so of course, I am also very surprised about how the AI is really capable of yeah, like deeply analyzing like my answers and then knowing all the basics of the language and try to guide you. Uh, so this keeps me even thinking of. So it's like, yeah, it's literally teaching me, right? It's not the other way around. So normally I should teach AI, but now AI is teaching me. All right, let's see what would be the next step.
Welcome to the course, Systemverilog Tutorials, Hardware Design and Verification. This comprehensive hands-on course equips learners with the practical skills needed to design real hardware using Systemverilog. Through a structured 4-module progression, you will master the fundamentals of RTL development, starting from basic modules and data types, moving into advanced constructs like structs, enums, and generate blocks, and culminating in the design of a fully functional digital calculator. Each module includes hands-on exercises, simulation-based assignments, and guided coding practice. You will learn how to model combinational and sequential logic, construct reusable parameterized modules, implement finite state machines, and write clean and scalable RTL. Along the way, you'll apply real engineering practices such as hierarchical design, clean coding standards, test bench construction, and modular verification. By the end of the course, you will have built a complete modular calculator system designed, implemented, simulated, and tested entirely in Systemverilog. Target learners. This course is designed for engineering students, FPGA beginners, RTL designers, and software developers transitioning into hardware design. It is also ideal for embedded engineers, verification interns, and anyone preparing for digital logic, FPGA, or ASIC roles that require Systemverilog proficiency. Prerequisites. Learners should have a basic understanding of logic gates and binary arithmetic, along with some familiarity with digital circuits or introductory HDL concepts. No prior Systemverilog experience is required, but comfort with technical problem solving will help accelerate learning. Modules description, Systemverilog foundations, and basic modules. This module introduces the foundations of Systemverilog RTL design, including how to write modules, use ports and parameters, work with common data types, and model fixed-size static arrays. Students will install the Quartus Prime software and build their first hardware blocks and begin implementing the arithmetic core of the calculator. Dynamic data structures, custom types, and operators. Learners explore dynamic arrays, queues, and associative arrays, test bench focus, create custom composite types using typedef, enum, and struct, and use Systemverilog operators to implement logic and arithmetic. The calculator project is extended with an ALU and operation selector. Sequential logic and state machines. Students learn how to design combinational circuits using assign, build sequential circuits using always FF, registers, counters, pipelines, and implement decision logic using if and case. They then build the calculator's state machine and control logic. Learning outcomes. By the end of this course, you will be able to design synthesizable Systemverilog modules and integrate combinational and sequential logic into functional subsystems. Implement an ALU, memory structures, and state machine-based control for real digital systems. Develop a finite state machine, FSM, to control complex system modes, calculator modes, user inputs, and operation sequencing. Simulate, verify, and debug Systemverilog designs to ensure functionality of the full calculator system. Proof of learning. To ensure you have mastered the concepts, the course includes the following assessment components. Hands-on labs. Each module includes a practical assignment where you apply module-level concepts such as designing RTL blocks, building data paths, or implementing control logic directly in Systemverilog. Assessments. A structured quiz evaluates your understanding of Systemverilog concepts, hardware modeling techniques, and design verification best practices through targeted questions. Final project. The final project requires you to design and integrate a complete Systemverilog calculator system, demonstrating your ability to apply RTL design, sequential logic, FSM control, and verification techniques in a realistic hardware development scenario. Tips for learners. Practice every coding demo inside Quartus Prime. Hands-on iteration builds intuition. Draw block diagrams before coding. Hardware is easier to reason about visually. Use waveform simulations to verify behavior instead of relying only on code inspection. Build modules incrementally, ALU, registers, FSM, integration, to avoid overwhelming debugging. Apply each concept to your calculator project. It strengthens long-term mastery. Build the skills to design, simulate, and verify real hardware systems using Systemverilog.
All right. So that was an overview about yeah, about the course. And
What if you could stop writing isolated system Verilog snippets that go nowhere and instead build a complete professional grade hardware system from scratch? Imagine going from a blank file to a fully working calculator model, learning exactly how real engineers transform design specs into clean, scalable, industry ready models. Hi, I'm Emmanuel, a hardware engineer with hands on experience designing digital designs using Systemverilog. I've spent over 7 years building modular, reusable hardware and breaking down complex design into practical, understandable blocks. Welcome to Systemverilog Tutorials, Hardware Design and Verification, created in collaboration with StarWeaver and Coursera. This course is designed for early career and seasoned hardware engineers who want more than syntax tutorials. Instead of isolated examples, you learn system Verilog by designing a complete calculator system from start to finish, just like you would in a real engineering role. We move step by step, turning concepts into working hardware. By the end of this course, you'll be able to design synthesizable system Verilog models and integrate combinational and sequential logics to form complete digital subsystem. You will implement an arithmetic logic unit capable of performing core operation and basic arithmetics for calculator functionality. You develop a finished state machine to control complex system, user inputs, and operation sequencing. You also simulate, verify, and debug system Verilog design to ensure functionality of the full calculator design. I'm excited to guide you through this journey, so let's dive in and start building real system Verilog designs together.
All right. So, I think that is okay for today. And yeah, thank you so much for watching and see you next time.